Welcome to this EELISA Innovation Talk. EELISA promotes some topics to all the community, of course, particularly our students, when we want them to know an important issue, a timely topic that we think they should be informed about and that is relevant. Quantum technology is the topic today, and this is one such topic. The European Commission is funding and supporting significantly this topic, but also national governments in Europe and abroad are doing the same. So we are here to present quantum technology to you. There's one further reason, because two of the universities that are part of this alliance, Scuola Normale and École Normale, are offering themselves as hubs for training in this topic. We have courses available to all the community, but also we have formal programs in a master's program and a PhD program that we offer to all the community. So thank you for being here. We believe this is important, and by we mean at least the 6 speakers of today. 3 from academia, of course, Scuola Normale and École Normale are represented, and 3 companies, a large one, IBM, and 2 small, for the time being, we hope, startups. One a spin-off of Scuola Normale, one a spin-off of the École Normale. Now, if my colleagues agree, I will smoothly move towards my presentation. And I was given this task that I believe is a challenging task, at least I find it a challenging task, that is to give you all some basic knowledge on quantum elements, what is relevant for quantum technology. Why I believe this is challenging is because our natural language, our very imagery, mental imagery, was built by our species in the millennia based on what we perceived of the world. We have a vision of the world that our senses provide us, and that vision is a low-resolution vision. To the best millimeters, but typically centimeters, meters, that's the type of reality we see. The quantum becomes fundamental and visible to a much smaller scale. For that, we have yet no words. We have mathematics for that, of course, but we don't have layman words to explain it. So that's my effort. That's what I'll be trying to do in the few 10, 15 at most minutes. Quantum technology is the technological offspring of quantum mechanics. Quantum mechanics is a century old, but still not part of everybody's culture. And so we have a little effort. But nature works with quantum technology all the time. That's how nature operates. The simplest example I could think of to show that is represented here by the periodic table of the elements. Very different things, very different objects, very different effects. We perceive copper, very different from nitrogen, very different from lithium, very different things. But if you think about it, they're not that different. There's a nucleus and a handful of electrons around it. But for some reason, despite the same basis, the final result is entirely different. Unfortunately, that's in the back of our mind how an atom looks like, a small planetary system. The sun replaced by the nucleus, the planets replaced by the electrons. Well, if it were so, why would be the elements so different? If you just add another spinning thing around it, why should they be different? It makes no sense. In fact, this picture is completely wrong. An electron is not a little gray ball spinning around the nucleus. Never. It's never a little spinning ball. It is something different that we have not seen. We have started seeing this thing only in the last 10, 15 years or so, literally seeing the quantum objects. And now we can modify the quantum objects and work like nature does. And that's quantum technologies, as I said before. Well, a first step towards how electron looks like is shown here. Some of you attended chemistry courses and know what orbitals are. Well, that is an electron. An electron around under the influence of the positive charge of the nucleus can be forced to compress in a small region and will look like what we call an s orbital or a p orbital that you see here. Those are the electrons. That is a better picture. A different shape of the electron means a different function. That's why nitrogen is different from copper, because the electron is packed in a different way. The electron is forced by the nucleus in a small volume. As a consequence, it can have only certain energy levels that we call S, P, D, etc., etc. And that's quantum technology operated by nature. We can now do the same thing. We can force electron in small volume in many different ways. Some of them you will hear today. When you squeeze an electron, it will exist only at certain energy levels. They're not called SP, they have other names, it doesn't matter. And they look this wavy, complex, articulate things that are actual electrons. That's what makes one atom different from another. But we can also build different things like this. Wire objects, these are very thin, solid objects. If we put an electron in there and we see how it looks, that's how it looks. Different shape again. That's what an electron looks if you put it in that support. Squeeze an electron in any way, you'll get a different shape and you'll get a different function. So starting from any material, by changing its shape, you can obtain a different property, a new artificial property. That is 80% of quantum technology, but that's normally labeled as first quantum revolution, and we'll be focusing mostly on the second quantum revolution today. Incidentally, if you look at this drawing here, and I say that the electron is confined by these barriers, but you see that the electron is getting into the barriers. Well, if the barriers are sufficiently thin, the electron will go out, will leak out. This phenomenon is called tunneling. And once again, you see the language problem. The original name is tunneling simply because when the effect was discovered, somebody said, well, if the little gray ball has got to go through, there must be a hole, there has to be a tunnel, from which a name, like a car going through a tunnel on the Mont Blanc. It's not true, there's no hole, but the electron goes through anyway. And this concept of tunneling is useful for us to learn something else of quantum technology. If we look at one electron in this blue box, and I put a thin barrier or any fluctuation where the black line is, you see this electron from the top or from the side, on the lower part. Let's launch this electron against this wall, thin wall. That's what happens. I stop the animation. You see, after the interaction, the electron is both at the left and on the right of the barrier. No probability, certainty. The electron is at the same time on the left and on the right. That's a second property of electrons. They delocalize. They can be delocalized in different places. A very important tool of quantum technology. Also this one. Or we can get fancy. This is the same electron, looks very fat, simply because I changed the scale. It's in the same box, this time is gray, and I launch it against a very thick barrier this time, with two holes. Okay? So thick that the electron cannot go through, but we have two holes. What does the electron do? Well, it goes through both holes at the same time. Not sometime left, sometime right. It's one electron. It goes at the same time through both holes. That's what they do. It's difficult for us to imagine, especially if you keep on thinking that the electron is the gray ball at the beginning. Then there would be no quantum technology if that was the case. This is how electrons behave. And why I'm insisting on this? Because this is an essential concept for us to move on and talk about quantum computing. What you see here is a sheet that supports electrons. If we send an electron from the left, it will have to squeeze through that narrow region, and then it will find an obstacle. By now we know that the electron will go on both sides of the obstacle at the same time. Then the electron finds a single way out here on the right. Well, the two parts of the electron must compose again, and the electron can go out. Well, this is not always possible. Although the passage and the hole is there, depending on the experience, technically we call it phase, that the electron accumulated in the two different paths, it will or will not be able to go through. If it is favorably organized, constructive interference, it will go through and will have current. If it is not well organized, we talk destructive interference, it will not be able to recompose and it will be forced to go back. So there will be zero current. So current or no current, 1 or 0, like in a transistor. And in fact, the most basic and elementary way to look at a transistor is a channel where electrons propagate. If we let the electron propagate, we have current, and this could be our logic state 1. Otherwise, if we act on this electron, we can just block it and not allow it to go through. The electron will not propagate, current is 0. We say that the transistor switched. These switches, 1, 0, is what make computer operate. With this binary logic, all sorts of calculations can be performed. Well, we have seen that we can obtain the same effect with constructive and destructive interference. And this is a slight change in topology, but this is how it looks. An electron delocalizes and can propagate if we have favorable conditions, constructive interference. Or with the same physical situation, it will not propagate. Okay? Also in this situation, therefore, we have on, off, and the bit is either 0 or 1, depending on which of the two conditions are in place. Incidentally, such a process is very energetically speaking effective. Stopping an electron this way is much, much easier, and it costs less energy and time than the previous example. But what I want to focus on is here. What is the bit here? Is it 0 or 1? Before we actually test it in this region where the parentheses are. Well, in that region, the bit is both 0 and 1, and that is a quantum bit, okay? It may look like this is useless, because if the bit is both 0 and 1, I don't know what to do with it. On the contrary, in the following talks, you'll hear how important it is. We have very effective algorithms to take advantage of qubits with respect to bits. And that's what we're going to be talking today. These are a few examples and some ideas I would like you to keep in mind. Electrons determine properties of objects. By changing the shape of the electron, we change the material and get different effects. This can be relevant for medicine, for construction, to make surfaces resistant to bacteria, you name it, whatever. All can be done. Electrons can be delocalized spatially, and they can be in these mixed configurations where they can be at the same time in one configuration or another, like a qubit being 0 or 1. Okay, I hope this was useful and a good code to decode the following talks. And the next speaker is a colleague from Scuola Normale, Vittorio Giovannetti. Some of you may want to ask questions. Under your YouTube on the ELISA webpage, you'll find a way to ask questions. We'll be happy to take them and answer them and discuss them with you at the end of all the presentation. So, Vittorio, the floor is yours.
Thank you, Fabio, for the very informative introduction. Okay, so I think we can start. Yeah, just a couple of minutes. Well, okay, thank you very much. And I'm Vittorio Giovannetti. I'm a professor of theoretical physics here at Scuola Normale, where I lead the research group on quantum information theory. But I'm also co-founder of one of the two startup companies that Fabio introduced before, the Planckian company. But you will learn a little bit more about the activity of Planckian later in the afternoon when Michele Dallari will give his presentation. Michele is also a co-founder of the company. So my aim today is just to give you a brief introduction to the basic notion of quantum information theory and to frame this interesting process in an historical perspective. So, as we have learned from Fabio, quantum technology and quantum information is a discipline. It started as a discipline, but now has been evolved into a technology development in which try to establish what are the fundamental limits and the possibility that quantum mechanics offers in storing, processing, and transmitting information. So, okay, fine. So, in order to understand a little bit what quantum information is, we need to move a step back, more or less the same kind of things that already Fabio have told you. We have to talk about quantum mechanics. Yeah. So quantum mechanics is a theory that was developed at the beginning of the last century, and it's safe to say that it's probably the most important building block of our modern point of view about physical nature. Indeed, this theory is the essential ingredient that allows us to explain essentially reality as we see now. All the other parts of physics are somehow connected with quantum mechanics, with the only exception possibly with of gravity, which still doesn't fit in this picture. But as long as you speak about material science, particle physics, nuclear physics, laser physics, superconductivity, all these disciplines assume at some level the structure of quantum mechanics. So that means that this is a very powerful tool. However, despite this enormous success of the theory, there are still some parts of the theory that are kind of puzzling. Yeah? This is part of what John Bell defined as the unspeakable part of quantum mechanics, because there are some principles that are associated with the internal consistency of the theory, which makes no sense from in terms of our classical intuition. And I'm referring here about entanglement, superposition principle, the things that Fabio have shown you a couple of slides ago. All this part makes absolutely no sense if we analyze it with our classical brain. So I don't have too much time to discuss about this effect, but let me tell at least about one of those strange phenomena that occurs in at the quantum level, and this is entanglement. So entanglement is a very strange kind of correlation that quantum system can exhibit, which has no classical counterpart. So according to these phenomena, you can have correlation between distant objects that indeed defy our classical intuition. In particular, such an effect are so strange that, for instance, Einstein, which was one of the founding fathers of the theory, considered it completely wrong. He was talking about this effect as spooky action at distance. He couldn't use the name magic, but he used, spooky action at distance. Yeah. And indeed, because of entanglement, many effects arise in the theory that goes under the name of pseudo-paradox of quantum mechanics. The most famous of one is the Schrödinger-Cat paradox. Now, we now know that indeed entanglement is a real phenomenon. We can measure it, we can detect it. And one of the main consequences of this spooky action at distance is that because of it, quantum mechanical systems are intrinsically complex. They are objects which are difficult to characterize and difficult to study. Now, more or less in the 80s, some theoretical physicists like Richard Feynman and David Deutsch introduced a new point of view on this problem. So what they were thinking is that maybe you can use complexity, you can use the very complexity of quantum mechanics to cure the complexity of the quantum world. Yeah? In other words, they were thinking of using entanglement as a sort of vaccine, yeah, that can cure our inability of characterizing quantum systems. And this was the birth of what we know now as quantum computing. So just to give you an example, yeah, so consider to have a quantum system like this object here, composed by n subsystems. Now, it turns out that because of those strange correlations that quantum systems can have, because of entanglement, if you want, our ability in describing this object using conventional computers, classical computers, is extremely difficult. Yeah? Essentially, you can prove that you need an exponential number of degree of freedom that would enable, that you have to use in order to simulate the dynamics of this quantum object. But the things change completely according to the view of Feynman and others if we try to simulate the dynamics of this object with another quantum object. Quantum objects have the same kind of nature, so they will easily allow you to simulate the dynamics of this first object here. Yeah? Now, of course, there is an important difference between the first quantum object here and the second quantum object here. So the first is the object that you see in nature, that you obtain from nature, and is the system of interest that you want to study. The second object here, instead, is something that you build. So it's a man-made object that still obeys to the law of quantum mechanics, that you can control completely, and that you can use in order to simulate the original one. In other words, this guy here is what we know now as the quantum computer. Yeah? So people started studying, at least theoretically, how these strange new devices could operate, and it was soon evident that they are possibly very powerful. They don't only allow you to simulate other quantum mechanical systems, but you can use them to solve many other problems of physical interest. So for instance, you can use them to solve complex numerical problems like factoring, but you can also use them to solve optimization problems, to synthesize new material, and so on and so forth. Yeah? So we now know that these kind of systems are very powerful, and indeed, as you will see from the other speaker that will follow me, we can now build at least some version of those devices. Okay, at the same time, it turned out people started realizing that you can use quantum effects like entanglement not only to boost your ability of computing, to design new machines that are more powerful than the traditional one. But you can use the same effect to boost other processes, like improve your communication ability. So you can build communication lines that exploit quantum effect, which are more efficient than their classical counterpart. And this is due to a series of phenomena that were discovered during the 90s by Bennett and others, like superdense coding, teleportation, and others. And incidentally, the same kind of effect, this same communication line have also grants you also the possibility of implementing cryptography in this communication process. In other words, you can devise communication lines which are secure even in the presence of an eavesdropper that try to interfere with the communication. And this is just because you are using quantum resources between the sender and the receiver of the message. But quantum effect can also have an impact in other sectors, like sensing and metrology. And so here the idea is that suppose that you want to recover some signal that I represented here with the symbol X. This is a parameter that you want to estimate, like the temperature of a system, or a phase, or a time of arrival of a signal. Well, it turns out that if you try to recover this signal here, you can try to improve the precision with which you can reconstruct that value by using quantum probes. That is, systems that are being prepared into spatial superposition that can kind of encode the value of this parameter in a much more efficient way than you can do in classical terms. Okay, so all this discovery, all these observation constitute a very broad landscape that I call here the quantum technology landscape, in which essentially you apply quantum resources to solve different processes, to improve different procedure, computing, metrology, communication, thermodynamics. And of course, the point is that this kind of landscape is still not yet completely known, is in part still uncharted. And it is our goal, your goal, if you are interested to get involved into this process, to find the proper way of moving and to chart and to establish the most efficient route in this landscape. Now, up to now, the professionals that were involved in this kind of research were mostly physicists and mathematicians and possibly computer scientists. But the need of creating a technology starting from this preliminary observation means that nowadays other professionals will need to be involved, like engineering, chemists, and others. And of course, it's very important that in this kind of endeavor, there will be a strong collaboration between academia and industry. Okay, so this is more or less what I wanted to tell you. I hope that have convinced you somehow that quantum technology is a very fascinating field, which is rich of possibility, and it has a lot of implication in many different sectors of everyday life. Okay, thank you very much. Yeah, so our next speaker is Carlo Sirtori. He's a professor from the Scuola Normale Superiore. Please, Carlo.
Thank you very much. Thank you for the introduction, and thanks for all of you who are listening at the moment, and for the present as well. We wait a second for the change of the presentation. So what I'm going to describe to you, it's a bit complementary to the end of what you just saw in the previous presentation. And it is to try to really, how do you say in quantum mechanics, to go on the subspace, to measure the subspace where we have really applications. And again, I mean, my name is Carlo Sirtori. I'm from the École Normale Supérieure. And I have a chair. I'm the holder of a chair that from Thales, that is Center for Quantum Devices. There you go. So it's what I want to show you also. It's sort of the historical moment, which is very interesting. Is the fact that obviously I'm on a chair of an industry, so but not just defending. My position. I think it's quite very interesting what's going on here. It's the technological breakthrough and the fact that actually, we have really we want to form a new generation of quantum engineers or scientists. And for this, actually, there is a really a magical moment that we have the convergence of industry and academia. This is, it happens regularly. One of the examples, for instance, in the 80s, when there were the development of telecom, where diode lasers and fibers were coming, and nobody were really thinking of how far we could go. And that's another moment where you have the industry fundamentally that is sort of soliciting the academia and universities in order to grab more knowledge. And then also, if you are very lucky, you can also show this to the Queen, but now the Queen is not there anymore, so it's going to be Charles for you, and to try to have it in your lab and showing. You see, this is 71, and Ramsay in England actually was really showing how incredible would have been to have this communication. See, 71 out today, everything is done in fiber, and it takes some time, and so that's also patience. Again, let me go again on this issue because I think it's very important, and it's the way that there was this shake hands shown by Vittorio just before, and I think it's very important. It is because there really is a trading. So industry, there's this quantum knowledge, very general on science, not necessarily only technology, and there's a need on one side. And there's the holder on the other. In the moment is at the Center of Research and Universities. And there's a profitable trading. It means that actually we can obviously have a financing, but also is the interest to get the knowledge from the industry and the capability of scaling up our invention. Not only make prototypes, but having this incredible knowledge that we have the industry today to transform and make products. There are two possible paths also, where we see this is the big industry, and we have then Federico Mattei after, and that actually is looking for this kind of interaction, IBM, Google. We have other industries, that Thales is as well, for instance. But then also there's another thing which is very important, is a big message that I would like to convey today, which is the fact of stimulate entrepreneurs and entrepreneurship, which is the possibility of creating knowledge and transforming knowledge into some products. One thing which is important, this shake hands is not philanthropy only. It might be sometimes, but most of the time it's really a trading of goods that are on both sides. Why quantum technology? Quantum technology, I think it really touches a lot the imaginary part of our brain because it's after having the electronics and all these performances, amazing performances that we have seen in technology, we actually have an idea of we are aiming for a breakthrough or for finally changing and moving toward our functions, new functions. Let's say that will be able to make something that is barely conceivable in our mind, and that's what we like, so to explore, to go farther. And we have, obviously, the quantum processor, quantum computing, it is the biggest part. We have, anyway, also new physical process for energy storage, and this is actually also what we see later. Quantum Internet, it is the possibility, again, of having, again, Quantum Internet, for instance, is one of the closest to realization. And then other things that are even more like, material for catalysis or teleportation, which is something, again, here we are having really at the farthest things. Teleportation is for photons, okay? It's not really exactly what we see there. But again, I mean, it's a reality, and for instance, teleportation is an essential part of all the quantum internet, and is the only possibility that we have fundamentally to beat losses and to, let's say, be able to cope without having amplification, which is an essential part, fundamental, of quantum communication. So there are three fields that I'm discussing a little bit with numbers, because are the one that actually I've been working on in the last couple of years with the industry to understand where are, let's say, the market, where we are planning of going. And you see actually they are forecast up to 2050. Now, but there are not going to be any more, but, I hope it's right. And you see, there are three we focused on, and I focused particularly on three applications, which are computing, communication, and sensing. Have been already introduced, so I'm not going to spend much time. And you see how computing is really where everybody would like to go, because it's fundamentally where is the biggest market. And that's the reason why industry is really, let's say, putting a lot of energy in this direction. There might be then changes, but fundamentally that's really what you see. And you see also that in terms of, let me see if I can find it. You see that computing, this is the total number of startups in the world in the last 5 years, if I remember correctly. So 233 in computing. And you see communication is after and sensing is the last one. Even then if you look at the, let's say the funding, you find pretty much the same, and you see that actually it's going to be even more squeezed, sensing and communication in the forecast. Those are forecasts that are not scientific, okay? So those are really forecasts in terms of people who can understand and project where to put the money. The quantum technology, again, it's those three things where I had data to show you a little bit what it, the way probably should go. And then those are the hardware for quantum technology, but it's very important also other two things that I'm not going to discuss today with numbers, let's say, but are the software, for instance. The software for quantum technology is not obvious at all. I mean, the software for quantum computing, we are still at the level of the assembler, but not even that. I mean, so we are really, the software, many times, it goes only with the kind of hardware that you are dealing with. So there's no a general thing. We're really starting now to have maybe some reference. Otherwise, we had a level of logic, which I think is very, very interesting. And also the other part is quantum materials, which is another way actually to try fundamentally to get better material for more energy harvesting, for instance. Now, I think actually I'm going to go fast on this because we're going to get a talk later from Federico, and therefore actually let me get more on the other part of quantum computing, which is this is not the quantum computing as we think, but is also a very industry extremely interested for two reasons. The first is technological inertia, which is what really we have to fight as a researcher many times, because industry try to change the least possible. And even in the computer today, the fact actually that the quantum effect are really, really small, even though the gates are 10 nanometers or 7 nanometers, is quite remarkable. But the other possibility, and still related to quantum science, for instance, I make an example which I think is very relevant and is neuromorphic computing, sorry, and which, again, it doesn't necessarily involve entanglement, or it doesn't necessarily involve all, let's say, the hardcore of quantum computing, but it's still very interesting, and surely that actually quantum effect that could push it farther. Now, the well, we have to do neuromorphic computing for sure because it doesn't move anymore. Let's see. Can I use this, maybe? Yep, okay. The other part that are important is the quantum sensing. And even though you see in a market, it might be somewhere lost in a small part, still actually we have fantastic things to do. And for instance, atomic clock, which is amazing today, what we do is 10 to the minus 18, we can know, the fraction of the second, which is 1 second with respect to the age of the universe. And then we have much more applied things. This is metrology, but quantum inertial navigation system could be extremely important. The fact actually to know how we will move on the Earth, but also on the space, which soon actually we're going to be in the moon again. Then we have a quantum magnetometer for biomedical, for instance. That would be very, very interesting. Quantum imaging also is absolutely interesting, which is very related to what I say on the bottom here, quantum LiDAR, which are fundamentally optica radar, also for pollution monitoring and ranging. Particularly ranging is the very important thing. Energy access and storing is the last thing that I want to discuss a little bit, or at least present, is material with high mobility. Could be an asset, for instance, for giant capacitors and making better battery, but also we have spintronics, which could really change and give us another idea of how to store energy. And today, honestly, the energy storage is one of the most important things we need to move towards the green transition. Quantum catalysis also would be hyper important, and it would be the possibility, for instance, as everybody knows, to break water into hydrogen and oxygen. And the last thing is also for instance, is this ability that we might have, and it's mentioned before, to move away from our hard physics and try to collaborate also, for instance, in biology and understanding, what is quantum in the photosynthesis. Now, this is really pretty much a conclusion. I go back to, which is a way to, encourage, to move towards, to try to make yourself free, because that's really also a reality. All the friends that I have that have been doing startups, they say to me that I couldn't have a boss. I mean, I do it because it's fantastic. I work as a mad, I do a lot of things, but at least, I do, and I try to realize my ideas. I think this is really, really a very good point. Also, another thing which, this comes from the United States, the NFF is no fear to fail, is something very important, and as most of us are good pupils and good students, we have just horror to, fail an exam, and then, in our brain, it stays like this for the rest of our life. In fact, actually failing sometimes is an important thing. And also, sometimes I have to say that it might be a little bit, this quantum technology might be very oversold sometimes, and that's all right anyway. The important thing probably is to dream and to have ideas and to really exploit this amazing possibility in the first to start seed and startup. Today are very well financed in Europe, in any country in Europe, and we have to take advantage. The difficulty can come years later on the scaling up, where probably actually we do not know exactly how to do it. But, anyway, this is, again, a way to say, don't be worried. There's a really opportunity to grab. if anybody wants to. Okay, and I close on this, and I leave the word to Federico Mattei from IBM. Thank you very much for your attention.
Thank you, Carlo. Good afternoon to everybody, the one connected on the web. So I'm Federico Mattei. I'm working in IBM Quantum, which is a division of IBM Research, an international division for IBM. In IBM, we are working on quantum computation, I would say, since the beginning, so since the 1980s. You have seen several quotes from articles from Charles Bennett. He is working from IBM. Now he's retired, but he's still working with us. So let's start. Of course, at the beginning, we had quite a small group on quantum, but starting from 2016, our group became larger because in that date, we built our first quantum computer of just 5 qubits, and we decided to put it on the web. There are different ways to build real quantum computers. At the moment, we are building quantum computing using transmons, so superconducting material, Josephson junctions of superconducting material. And I would say a couple of things about the state of the art of our hardware and our software, and then I will close my short speech about our collaboration with academia and with the other industries, which has been already cited, and we think which is really the core of the research today, to collaborate all together in a single ecosystem to push the limit of quantum computation and to arrive to the quantum advantage, so the moment in which we can use quantum computer to do science, and we will use quantum computation to do research, and also to do business. So, first of all, there are no standards to measure the performance of a quantum computer at date. So we decide to set our own standards, and of course we share it with all the community. So we measure the performance of our system on these 3 dimensions, and we think that to reach the quantum advantage, we have to rise all these 3 quantities all together at the top. So we think that superconducting materials, for the moment, is the best technology to rise together all these quantities at the top. Of course, there are other technologies which are very interesting. Some of them maybe have a better quality, but having a better quality, they sacrifice the other dimensions. So the scale is the number of qubits. Of course, we are rising the number of our qubits. At date, we have 433 qubits on a single processor, and we are going to announce, we will see in a couple of charts, the first processor with over 1,000 qubits on a single chip, and it will happen in 1 month. We measure quality. At date, you know that all quantum computers are noisy, so we have to manage errors in our quantum computer. Quality is measured with quantum volume, which is a quantity which sum up all the different errors you have in a machine. And we are doubling the quantum volume of our system. At the moment, we have 500 of quantum volume. Other hardware producers are measuring volumes of quantum volume of our system. As I already said, for example, with ion traps, we are having better results than this. But they are not having the same result, for example, on speed. Speed is another important quantity because a lot of quantum algorithms, in particular quantum algorithms applied to the business, have a short time frame to be executed. I think on the application to financial market, so portfolio optimization, risk management in banking sector, or I'm thinking on logistics. So you have to plan the logistics of your van during the night because during the morning they will start going. I'm thinking about, for example, the weather forecast. Of course, you have the night to forecast the weather of tomorrow morning. So we measured the speed of our system with CLOPS, which is we stand for circuit layer operation per seconds. And at the moment, we have 15,000 circuit layer operation per second, and we are rising this number. And we can obtain this number on speed just with superconducting material, because the other ways you use lasers to control the atoms, and it takes more time. We have also a software kit, which has been donated to the open source community, so it doesn't belong completely to IBM, but we are the main contributors. Qiskit is an SDK based on Python, so you can use Qiskit to program quantum computers on Python, not just IBM quantum computers, but also other ones. There are basic commands to build circuits in the Terra module of Qiskit. And then there are also libraries with a higher level of abstraction to build your program without programming Qiskit at the assembly level, but going to a higher level of abstraction. This is our most important asset, which is the quantum computing roadmap from IBM. The layer at the bottom, which is in the dark blue, regard the systems, so the hardware. As you see in 2023, our commitment is to release the Condor processor, which has more than 1,000 qubits on a single system. And we are waiting for the 4th and the 5th of December, when we will have the IBM Quantum Summit in New York, and we will do our announcement for this year. But we will not stop here. The next steps will arrive in 2025 to have more than 5,000 qubits on a single system, and then we will continue in the following year up to 10,000 or 100,000 qubits on a single system. On the top, you see that we have also roadmap for software tools for different kind of developers, for the kernel developers, which are the developers which are more close to the assembly level, and also to algorithmic developers and model developers. Well, the last minutes of my talk will be around our collaboration. We will never have the possibility to reach this level of understanding of quantum mechanics of quantum computation without our ecosystem. We work strictly together with the open source community, with academia, and with industries since 2016. So we are really doing open innovation around this kind of technology. At date, we have more than 500,000 users on our systems, on our quantum system, which is really a high number for a technology which doesn't reach the production level at the moment. We have more than 25 quantum systems on the cloud available to industry and academia. More than 2,000 scientific papers have been published using our tools, our quantum computational tools. We have also an IBM Quantum Network, which is a more restricted team of institutions, universities, and enterprises working together with us. And we have 250 members of this community. From the industrial point of view, there are several industries working together with us. From banking sector, we can see here Credit Mutuel, HSBC, Goldman Sachs, JP Morgan, and others. but also telecommunication companies like Vodafone, energy and utilities like E.ON, petroleum like ExxonMobil, and much more. So different industries are collaborating with us to push the research on quantum computation. And this is my last chart. We are also collaborating with different states which signed a partnership with us to have IBM Quantum Computing on site, on the nation ground, in order to give the possibility to small and medium enterprise and to the university of the state to leverage this asset. The first nation to start build this kind of relationship was Germany in 2018, and they have their own computer working since 2020. And then we have Japan, Canada, South Korea, and Spain. And we hope we will have the possibility to have other quantum computers all around Europe and all around the world to give the possibility to scientists and to enterprise to work on this technology and to push this technology to the production level as soon as possible. So thank you very much for my time. I will leave the stage to Michele Dallari from Planckian, which is a spin-off of Scuola Normale di Pisa, as far as I understood. Thank you very much.
Okay, thank you very much. As we are approaching the end, I try to squeeze my talks in less than 10 minutes, so I will just give you a brief presentation of what we are doing as a new incorporated company, a spin-off, and then share with you what our lesson is during this startup journey we are currently doing. So here at Planckian, basically in a nutshell, we are working at the intersection of quantum and energy by developing quantum batteries. So it's a device, basically we are building engineering quantum device which exploit quantum properties to achieve superior performance in energy manipulation. Of course, since we are talking about quantum, meaning energy at nanoscale, since it's manipulation of very microscopical and quantum object. Of course, I talk about here about current quantum technology. Of course, quantum technologies are something that is still pretty new, but if you look at the second quantum revolution, as been well explained by Fabio and all the speakers before, this technology like quantum computing, communication and sensing are born out of the abilities from an intersection between quantum mechanics and information theory. So basically they exploit quantum mechanics to achieve superior performance in information processing. Now, in the last, I would say, 10 years, a new research field has emerged, which basically start to questioning whether quantum mechanics properties can be exploited also in the energy manipulation. So how we can exploit quantum mechanics to achieve superior performance of energy manipulation. And one of the first results has emerged in the so-called energy storage. So meaning that we can exploit, from a theoretical point of view, we can exploit quantum mechanics to achieve superior advantage in energy storage. And this comes out from what we are doing here at Planckian. So basically, if you think about quantum batteries basically are batteries that are rethink from the basis, from the foundation. And this has a network of qubits. So basically, a qubit, as we talked before, I would say, in our technology, they are built up upon solid-state architecture. And what is come out from our research that we are going to explain later is that basically you can exploit quantum mechanics so that you can have a collective enhancement of charging power. Meaning that the more qubits you have in the device, the faster is the shorter is the timeline that they need to move from the ground to the excited energy state, from the lower energy state to the higher energy state. This, of course, come out from also, I would think, a decade of research activities in the field, starting with the first architectural proposal in 2018, which go along to 2020, from these two guys, Marco Pollini and Vittorio Giovannetti. Vittorio is the guy I talked before, and is a full professor, professor of condensed matter physics and quantum information. And this set the ground for our activities from an industrial point of view. We started the spin-off process in 2022, so basically last year. We closed our pre-seed round of 2.7 million this year. So this is so basically it's this year, 2023. And then we start to build up a team, Stack of Brain Power, in 2023, so this year, with almost over 70% of people that are earning PhDs. And I'm just trying to close my brief talks to share with you what we think are the quantum essential. So basically what you need, what it takes to build a quantum startup. First, you need a credible roadmap. So quantum technology is meaning navigate uncertainty when you build potential groundbreaking technologies, but you need a credible roadmap because you need to engage investors, you need to engage people, you need to engage talent, and you need to present a credible roadmap. Also, but just saying and just sharing with people that this is an uncertain technology. We don't know where we're going to go in the future. Second, you need to educate the stakeholders, meaning not only university, you need to educate investors. What does it take to build a technology like quantum technology? So computing, sensing, also battery. It's a deep, deep, deep technology, meaning you need more than a decade. Sometimes, as Carlo showed before, he showed the life cycle of investor. Usually, to build this kind of technology, you need more than 10 years, which usually is difficult to match with the expectation of investor. And third, you need talent with, I would call, T-shaped background, meaning that you need talent, you need to attract talent with have a very deep expertise, but at the same time, they are curious, they're eager to challenge themselves, to face new information and to decide with the minimal information. And last slide, share with you what is it's a call of action for you, all of you guys, all of you young students, to why it's the perfect time to join a quantum startup. First, because it's a uber rewarding profession. You can have a uber rewarding professional career in a science-driven environment, meaning that you can challenge yourself doing science and produce technology, which is one of the most, I think, rewarding opportunity for people that come out from a very scientific background. Second is that there is no other technology, no other sector as of today where people have the opportunity to shape the direction of this technology, as in quantum. Maybe I can think about nuclear fusion to have some, you can find some similarity, but basically there is no other technology as of today as in quantum where you can have a direct impact in shaping direction of the technologies. And third, that it's one of the last, I think one of the last remaining sector when you can work with people that are like-minded, like you, and you know, especially people that have experience working in a corporate sector, sometimes is challenging to find people that you consider to be like-minded like you, but in the quantum you have surrounded by people like you, and you need people that have the same vision, but can come from different background. So I will ask all of you to think about this path as a potential career opportunity to join them in the quantum world. So thank you very much. And I leave the floor to Sebastian.
Just should I share my screen or?
Yes.
Yes. Okay. Perfect. Wait a second. Just switch up. Yes, I'm almost there. Give me one more second. Okay. All right. Do you see it? Can you just give me a go and then?
You're okay. We see you.
Thank you very
It's
much.
fine now.
So first, let me thank you for giving me the opportunity to present Alice and Bob today. So Alice and Bob is a quantum startup whose mission is to build a universal and fault-tolerant quantum computer using Schrödinger cat qubits. Maybe to start with who we are, we were founded in 2020 by Theo Perronin and Raphaël Lescan. So basically, Alice and Bob is a result of the PhD work of Raphaël, and the entrepreneurship of Theo, who was also a PhD student, but really with this entrepreneurial mind. Basically, they were, so I think it's interesting for the audience here, they were a very nice theoretical proposal saying that with cat qubits you can make great and very efficient quantum computers, and there were a few experiments, but none of them were working very well. And basically, Raphael, during his PhD, was able to have a very successful experiment. And basically, this experiment and the willingness of Theo started all this story. And since then, so we have filed something between 15 and 20 patents. We raised 30 million euros of money. We have partnerships with 3 academics institutions in France, and we are now 70 people. And maybe a few words about these 70 people. Most of them are working on the R&D, because indeed it takes quite a lot of people to make a quantum circuit like this one. You need to have a theory team who will design Hamiltonian and Lindbladian. You need a good software team, because now everything is using a software at some point. We have microwave engineers for the simulations, of course, a team for nanofabrication, some people operating all the infrastructure backend in terms of cryogenics and so on. Many quantum physicists, experimentalists more precisely, who are measuring those circuits and try to improve them. And yeah, to say a few more words on Alice and Bob, we are located in Paris. We also have a lab there with a few dilution refrigerator, control electronics, and so on. And yeah, so what do we do? First, as you know, there's an incredible variety of experimental platforms to perform quantum computing. It goes from spin qubits to photons, going through cold atoms or trapped ion. And in our case, we are using superconducting circuits. Yeah, and I wanted to emphasize that the biggest challenge we are all facing is how to escape decoherence. And this is well highlighted, as you know, by the Schrödinger cat soaked experiment, where you have a box in which you put a cat and some poison, and you have a mechanism that would release the poison depending on the radioactive decay of some atom. And basically, quantum mechanics tells you that the atom can be in a superposition of decayed or not decayed. And so this mechanism would mean that the cat is in a superposition of being dead or being alive. And you really cannot tell whether the cat is dead or alive before you open the box and look at the cat. But obviously, in the real life, it does not work. It does not work like that. The cat would be extremely fast projected on a dead or alive state, and the reason is that the observer is not only the physicist doing this experiment, but it's actually the full universe. So if even a single photon goes out of the box and hit a molecule in the air, the cat would be projected in dead or alive. If there's the tiniest sound or the smallest vibration, the smallest photon going out of the box, that will also decohere the quantum superposition of the cat. And actually, it's the reason why we cannot observe this state of the Schrödinger cat is also the reason why quantum computing is very difficult. If you want, this cat is somehow the state of the quantum computer, and all the environment of the quantum computer, by destroying decoherence, is creating errors on the quantum computer. And yeah, and if you put numbers, it's terrible. In particular, if you compare to classical computer, for instance, if you take the RAM memory of my computer, typical numbers would be that the error rate is like 10 to the minus 25 per operation. So, I mean, on a single day, there are just a few errors which are totally negligible. Now, if you take, sorry, it's not switching. Now, if you take one of the most advanced quantum computer, for instance, the one of Google in superconducting circuit, the error rate is no longer 10 to the minus 25, but 10 to the minus 3. And so in something like 20 operation with a 50 qubit chip, you have a completely random result. So the solution that people invented and I mean, theorists invented and experimentalists are now trying to do is a quantum error correction. So, for instance, a famous code is called the surface code, where you take your transport qubit, like the one of Google or IBM, and then you would put many of those qubits in a dense grid, in a dense 2D grid, and basically you put all those qubits in exactly the same state, and you will perform measurements a bit everywhere in order to be able to detect when one qubit is making an error and then correct for it. But the thing is that the overhead to do that is absolutely massive. For instance, to make using the transport qubit, like state-of-the-art transport qubit, if you want to have a single working logical qubit, you basically need a grid of about 1,000 physical qubits for it to work. So it's we have seen in I mean, 2 presentations ago by IBM that the kind of number of qubits we start to be able to fabricate, but it's definitely massive. And at Alice and Bob and with a few others, we are trying another approach where basically we encode quantum information, not just in a qubit, but in an harmonic oscillator, a quantum harmonic oscillator. And basically we use the massive Hilbert space of the quantum harmonic oscillator to implement the first layer of error correction directly at the physical qubit level. And I'm not going to say many things about it, but just to highlight what's good is with it, for instance, with the case of cat qubit. So here we are measuring the bit flip time of the cat qubit as a function of the number of photons in our harmonic oscillator. And we see that the bit flip time scales exponentially with the number of photons. And for instance, like at small number of photons, we have a bit flip time of a few microseconds only. But just by putting more and more photons, we see that this number is increasing exponentially up to tens of seconds. So it's many orders of magnitude higher. And so here you really see, and here it's with a single physical qubit. We don't need to have a chip with tens or hundreds of qubits, just a single one, and we can already increase. So this basically demonstrates that it's possible to implement a first layer of error correction at the physical qubit level. And then we still need some active error correction on top of it, but with a much smaller overhead. Okay, so I'm not going to say anything more about it. And let me just thank you for your attention.
Okay, thank you, Sebastian. And of course, we are now at the end of this webinar, and there are many thanks that I have the privilege of extending. Of course, from EELISA, the University Alliance, to all our speakers, and to from Scuola Normale too. Thank you for being here. We are leaving this on the web, so people will be watching this also in the future. After this October 30th, we are meeting here. We are there. You have our contacts, and we are happy to hear from you and get feedback from you about this. Our plan was to get you interested and motivated in what we think is a very, very important and timely field, in line with our innovation talks, and hope we have achieved this message. And with this, thank you very much for listening.